some things that we are doing whose aim is that we want to control quantum systems. And we want to control them in a way to either build extremely precise sensors, meaning sensors that can send an individual nuclear spin, for example, and also for perhaps quantum simulations. Okay, and so that's what happens in Ulm. And so, I mean, here's an overview of all the things that we are doing, and I will sort of focus a little bit on this, namely sensing single spins with diamonds, and also cooling quantum systems, which is a precondition for doing these sort of things. And the rest I'm not going to mention. So, what I'm explaining here is a novel kind of quantum sensor that uses actually something like that. Not quite as big, because that has 42 carats and it's really, I mean, it's really a very special diamond. I've forgotten the name, but it's a bit expensive for physicists. And so the point about this is a very, very pure diamond. So I mean, that's one of the reasons why it's so famous, not only its size. But even though it's pure, actually when you look very closely, it has defects. It has small places where it is not a perfect diamond lattice, but where, for example, one carbon atom has been replaced by a nitrogen atom, and the neighboring carbon atom has been knocked out somehow, and it's empty. And so that's an NV color center, it's called. And the name color center is simply because this actually, if you have enough of that, this gives color to diamond. So in fact, when you have a diamond that it really is perfect, then it is essentially transparent and you will not see anything. I mean, you will see through it. If, however, it has all sorts of defects, they can give it various colors. And so that means that these defects will also interact with light. Okay? And so you can shine light on them, they will absorb it, and they will also re-emit it. And so you can use light to probe properties of these defects. And in many respects, these defects will actually behave like atoms. Okay? So as you can see here, there are level schemes, there are ground state, excited states, they have an electron spin, they have nuclear spins, and all of these things can be manipulated. And the neat thing about this is that although this is, so to speak, an atom sitting in a solid state, a piece of diamond in this case, it is actually rather well insulated from its environment, because diamond is very hard, for example, so vibrational frequencies are very high and therefore not very excited at room temperature, and it's a very regular lattice, and altogether it has a lot of useful properties. This has been established over the last about 10-15 years or so, that this is really a wonderful system, and it has another advantage. This is just sitting there. You do not need an ion trap or an atom trap or any very complex device to hold this somehow in free space and cool it and all these things. This is at room temperature in a diamond. You can take the diamond, you drop it, you pick it up again, it's still there. So that's quite a big difference to an ion trap also, where you have to spend considerable effort to actually keep your ion where it is. Right? So that is neat. Of course, when you drop it, you have, I mean, it will not change its place, but you have to sort of locate it again with your laser, but it's really unchanged in position. And the nice thing is also that people nowadays can start and create these kind of defects in a controlled fashion. So one way is that you take a mask across this diamond with tiny holes, and then you send, for example, a nitrogen beam, a beam onto the diamond. The nitrogen will hit the diamond, it will enter it, will make a little random walk, at some point gets stuck there. And because this is a forceful event, there will also be carbon atoms knocked out of place, and then there are various techniques, annealing and so on, to try and make sure that these defects wander, and then at some places there you form these empty centers. And then you have to look for them. So that's the standard way at the moment. there are ideas of how to use ion traps actually to make this in a very, very controlled fashion. You take an ion trap, you laser cool an ion in there to absolute, well, almost zero, and then you shoot it out of the trap into the diamond with a very high spatial resolution. So this is work that Ferdinand Schmidt-Kauer and Mainz is actually carrying out, and it's sort of progressing well, and that would be a very beautiful way of making little arrays of NV centers in the diamond. And I will come back to this in a moment. Anyway, so what I want to do here is something, well, I'll build this up. So first I will talk about a single NV center in such a diamond, and that's easy to prepare and it's easy to find. And what I want to use this for is actually as a magnetic field sensor, but as a very, very, very sensitive magnetic field sensor. Just let me go back. The reason this will work is that down here you have an electron spin, and so you have energy levels that depend on the magnetic field. So if you have a magnetic field, these energy levels will shift, and so therefore you can, if you apply a magnetic field, these levels shift up, and then you can read this shift by optical detection afterwards. So you send a laser beam onto the color center and read out this energy shift. So it's clear that somehow this could work as a magnetic field sensor, but of course you have to show how well it works. And so there are some, in principle, I mean, some demonstrations that in principle this should work, and so there are pioneering work by Fedor Jelecko and Jörg Brachtrup in Stuttgart, and Fedor Jelecko now joined the University of Ulm, and we are working together to move this forward. And so the idea that you might want to have is, so you have an AFM, and then you stick at the end of it a diamond, but not of course a big diamond, but actually a nanometer-sized diamond, which contains one of these defects. And then you move it around, and then you try and sense nuclear or electron spins that are somewhere outside of this diamond. So that's the goal. And the applications will, for example, be in quantum information processing. You want to read out some solid state spin from some device. Or what I'm particularly excited about is applications in biology, where you can follow the dynamics of individual molecules with an unbelievable precision. So I'll come back to that. And so they, in an experiment, they have shown that in principle with such a device you can sense some magnetic fields, but of course they have not achieved this wonderful precision that I was talking about now, sensing a single nuclear spin. And the reason is that this is rather challenging. So you can imagine, I mean, an electron spin is already quite small, a nuclear spin is even smaller. So it's a small magnetic moment, it creates a small magnetic field that you have to sense, and therefore you need long measurement times. And if you have long measurement times, then you become sensitive to all sorts of noise, even if this is a very clean device in a way. I mean, if you measure for long enough, you will also see all sorts of noise. And in addition, if you apply this, for example, in condensed matter physics or biology, what you also have is you want to sense a nuclear spin or an individual spin in an environment that is not very quiet. So there might be thermal noise, there might be all sorts of motion. So it's not completely quiet environment. And so you have to do something about this environmental noise. And so you have to find strategies to get rid of this environmental noise, but also in such a way that you do not remove the signal. Yeah, you want to sense a magnetic spin, but you do not want to see the noise. But often when you use sort of techniques for getting rid of noise, you also get rid of the signal. So you have to think a little bit how to do that. And also, what you really want to do is you don't only want to sense that somewhere there is a spin, you actually want to know where it is. And ideally you would like to know this with nanometer or even angstrom precision. So that's a big challenge. And so there are various ways of attacking this. So first thing is, I like to call this the hardware approach. That's what, let's say, experimental physicists and chemists would do. They would make the device itself as clean as possible. The surfaces will be perfect, the diamond should have no defects, there should be no other unwanted nuclear spins in the diamond. So they will make, for example, an isotope pure diamond that is consisting only of carbon-12, and because carbon-13 has a nuclear spin that fluctuates and makes noise. So all these kind of material design and surface improvements and all sorts of things, that's what I count as hardware approach, and that's the first thing that one has to do. But if you do that, you will only achieve so much. You cannot make a 100% pure diamond. You will always have a little bit of thermal noise. And often when you want to sense your nuclear spin, it's sitting in an environment that itself is noisy, and you cannot just clean this up. I mean, if you want to measure a biological system, if you want to get rid of the noise, you have to get rid of the entire biological system, and that's not the point. You want to actually measure in that system. And so therefore you have to develop additional strategies. So it will really only, I think, it will only work when you have this hardware approach, making the device as good as you can, and then whatever that noise is left, that is unavoidable, you have to treat in the kind of a software approach, I like to call it. And in our case, this would be you use external radiation, microwaves for example, to make the system immune or less susceptible to the remaining noise that you have there. And so I want to explain you, just without too many details, some basic ideas of how you might want to do that. And some of this has just been demonstrated in the labs and all. So now I will get rid of lots of the energy levels, and really what we want to think about now is we have here a spin. This color center represents one spin. This spin is an electron spin, and it will be used to sense other spins. And if this is in a magnetic field that you apply externally, then you split all these energy. Then you split all the energy levels that you have. You have the m equals 0, m equals -1, m equals +1, and you split them so that you have a nice, clean two-level system. So that's the first step to make the system a little bit easier. So really, from now on, I will only talk about this level and about that level, and they are magnetically sensitive, and I want to measure this. Right. That's the first thing that you have. But now, of course, you have environmental noise. And this means, actually, they are sitting somewhere, some fluctuating magnetic fields or spins or so on, and they will make these energy levels here change up and down in a random fashion, so they lead to light rolling and noise. And so this leads to a loss of phase in this electron spin, and this is what you want to avoid. Right, so what could you do about that? And now here comes one possible approach towards that, and that is that you translate these phase fluctuations in amplitude fluctuations that cost you energy. So now, when I do this, now the environment to create such a fluctuation has to actually do work. Okay? And so how do I do that? Well, I actually take these two levels here that are nicely separated, and I shine on them a microwave field. Quite a strong microwave field. And that leads to a dressing of those states, so our best is always then to go to the new eigenstates of the system. So you have here the ground state, excited state. It's driven on resonance. So the new eigenstates of the system are coherent superpositions of ground and upper state and the antisymmetric superposition. Right. So that's just a basis change, but now the interesting thing is that what was phase noise here, phase fluctuations here, is amplitude fluctuations here. If I flip the phase between 0 and 1, then I go from this state to that state. Now, these states have an energy difference, so that means that if the environment now tries to interact with the system, it will have to provide a certain amount of energy to bring it from here to here. Now, what if the environment doesn't have enough energy for doing that? Well, if it doesn't have enough energy for doing it, then there are no transitions. And the system here, this electron spin, will stop interacting with the environment. Now, when can that be the case? Well, this can be the case when actually the environment, the fluctuations in the environment have a certain structure. So the environment fluctuations actually have a spectrum that is not white and broad, but actually is rather narrow. It has a certain spectral width. That's actually the typical thing that will happen in the situations where we want to measure. So there are all sorts of fluctuations in the environment, so the environment tries to sort of shape this system here with certain frequencies, and these frequencies are split, sort of distributed across a relatively narrow range. So each of these frequencies represents a certain energy. So if I split these two energy levels in stress states sufficiently much, namely much, to an energy difference that is larger than all the frequencies that are typically in the environment will not be able to perturb this spin, this system anymore. So in this way, we can actually decouple our electron spin from the fluctuations in the environment. And this is very similar in a way to this, what is known as bang-bang control, for example, except that it has the advantage that it's really a continuous drive. We switch on a microwave, and this will run for the entire experiment, basically. This is easier than sort of banging the system with very brief, short, quick pulses that have to be very intense. So in fact, we are sort of thinking about also a proof, so to speak, that this is the way to protect the system with the least amount of energy deposited in the system. So this is something that we are thinking, and we haven't proven that, but it might well be true that this is really the most energy efficient way of protecting against fluctuations from the environment. Okay, so right, so far this is only talking about the sensor, but now we have to actually watch out, because what we do not want to do is that somewhere in the environment now there's a nuclear spin which has also some frequency with which it will interact with the electron spin of the MV center, and if we also decouple from this, then we haven't gained a bit, right? So now what do we do? Well, so we'll have here a nuclear spin somewhere in the environment. And in the end, I want to find out where it is sitting relative to my sensor. So this is a nuclear spin. It creates a magnetic field, and that will interact with these two levels. And to make it interact in the most optimal fashion is to apply yet another magnetic field at the side of the spin, such that the two levels of the nuclear spin are split up by an amount that actually equals exactly the splitting of the electron spin in the MV center. And if you have exactly this matching of energy differences, then of course you are on resonance between these two, and any interaction will have a very good chance to actually affect both systems. So that's the idea. So on the one hand, you tune your sensor out of the energy spectrum of the environment, then you use a magnetic field to tune the spin that you want to see to the resonance frequency of the detector. And these two things together can make for a rather nice, relatively noise-free sensor that is generated by, well, this kind of software approach. Now, so that's the idea. You have to do, pages and pages of calculations, of course, to see whether this really all works out. I want to show you that how this could work. And so the goal will be, so here's our sensor, here's our nuclear spin, and this nuclear spin in this particular case will be phosphorus. We have chosen that because it has a large nuclear spin, so a large momentum, magnetic moment. And so, as a trial molecule, we have used phosphoric acid with this phosphorus 31 in here. And so now we want to see, at a distance of 5 nanometers, here's our sensor, here's the phosphoric acid molecule, and we want to determine the position of the phosphorus nucleus. Okay. And so I've explained to you how we want to do this, switch on these magnetic fields, the radiation, all that stuff. So let's do that. That's the schematic drawing of that, of the pulses that you want to use. And when you do it, you see this. So this is a map of a signal that you would see that indicates angle versus the polar axis, and that's in the XY axis. And well, actually you see that it doesn't work at all. So this contains no information What you would have liked to see are some specific blobs at some particular place which tells you where the nucleus is. And the reason is that we have forgotten something here. And that is that this phosphoric acid contains hydrogen. Hydrogen has a nuclear spin. And these nuclear spins are very close to the phosphorus. So they will actually, this nuclear spin will interact with this nuclear spin at a rate that is actually higher than the interaction of this phosphorus with our detector. So what we have to do is actually, we have to do the same thing as before. We have to decouple these hydrogen atoms from the phosphorus atom by, again, applying, well, there is a magnetic field already. They have different nuclear spin, magnetic moments, so they split up in different ways. And so we shine in a field that is on resonance with the hydrogen atoms, and in that way actually decouple them from the interaction with the phosphorus. And if we do that, then we get this. And now you can actually determine where this nuclear spin is relative to your sensor. So this doesn't tell you about the distance, it just tells you it is there or there or there. But we can also actually determine the distance in a very similar way. And so in the integration time here of 3 milliseconds, over a distance of 5 nanometers, we can see this nuclear spin and where it is. That also tells us that we can actually, if we want to, we can follow the motion of that nuclear spin as long as it's sufficiently slow, namely on the millisecond time scale. So if they were to move here, as long as we have sufficient integration time, this picture will just change over time. And so we might be able then to follow the motion of a nuclear spin or in a biological molecule when it is changing its shape, for example. Of course not when it's a rapid change, but some of these changes are slow and we can follow them. Okay. You can also do other things. You can actually choose not to measure exactly where the spins are, the nuclear spins are, but you can measure the distance between two nuclear spins in the environment. And so if we determine all the pairwise distances between all the nuclear spins in a molecule, then in principle we can invert this back to the structure of that molecule. And so you could dream, this is I think very challenging in the end if you do want to do this with large molecules, but you could dream of using such a sensor to determine the structure of large molecules, for example, on an individual specimen. You do not need to have 10 to the 20 of them or 10 to the 13 or so in an NMR device. You do it on an individual one. You do not need to crystallize them necessarily. And this is a challenge. I mean, a molecule that or protein that you cannot crystallize, you have a bit of a hard time to determine its structure, for example, in an X-ray spectrometer and so on. So this is an attractive possibility. Now, what I've shown you actually is working in principle, but we have made one little assumption, and namely that these driving fields that we apply, these gigahertz of radiation, that we use to decouple is perfect. That means it's really monochromatic, its intensity does not fluctuate over time. Now, for a theoretician, that's fine and well, but in the experiment, that can become a problem because every radiation source has certain fluctuations, and it's not necessarily so easy to stabilize against intensity fluctuations. So, let's say your driving field actually fluctuates in intensity. What does that mean? Well, you have here your original system. You have phase noise from the environment here. Now you continuously drive this with this field omega 1. And so you have to go to these stress state phases, and the energy splitting here is proportional to the Rabi frequency of this drive. That means if this continuous drive here is changing its intensity, it's changing its Rabi frequency, so the splitting will change. And so you have again some kind of noise here. Okay? And now you can ask yourself, well, okay, can I protect against that noise? And this will become an important question when you have to drive the system very hard. If your environment is rather broad in the frequency apply a very strong driving field, and the stronger the driving field, the more noise it actually introduces itself. Right, and so the name concatenated noise protection already tells you what you're going to do. Well, if it worked so nicely here to protect against these fluctuations, well, let's protect against these fluctuations by applying yet another field that is on resonance with these two levels and is irradiated in a direction orthogonal to this first field. So this was, let's say, the x direction, and here you apply a field in the y direction. And now this will protect against the fluctuations that are actually introduced by the first driving field. Okay. And so you can oops, nothing happens, right? Well, I forgot to switch off the animation. Right, so you get another set of states. They are sort of doubly dressed now, and they will be very much quieter. They will be protected against the environmental noise, and they will be protected against the noise that comes from the first order drive. Now, the second order drive will usually be much weaker, so it introduces less noise. Okay, but there might still be some noise, so you put the third field, and the fourth field, and the fifth field, if you want to. And then you can reduce the noise quite a bit. Don't know where this is now. So you can do this, you know, in this concatenated fashion, and in principle, theoretically, you can actually arrive at a completely noiseless field by noiseless qubit by applying just a few microwave fields of different frequency. Okay. And this frequency must be well chosen, and that you can work out how this works and what this is in theory. Okay, so this is something that we actually now realized in experiment. So basically, I don't want to go through these details here, but basically we did an experiment where we first only applied a single field to protect the system against noise. Then we got a certain improvement of the decoherence time, and then we switched on a well-chosen second field, and you can see that actually the decoherence time increases a lot, so that it means that the system is better protected. So these are the results. This is real experiment now, not theory. So here you see oscillations, and you see actually that these oscillations have a T2 time of 2.5 microseconds. So that means, so basically the phase coherence lasts for 2.5 microseconds in the system. And this is already benefiting from some protection, namely from one driving field at a rate of 40 megahertz. Okay, and then we switch on, we switch on another field, which is, well, I mean, the intensities differ by 30 dB. And now actually you see much longer lasting sort of coherencies. I mean, you see revivals as well. And the result is, when you actually work out what is the T2 time, you will see that in this case the T2 time has increased from 2.5 microseconds to about 25. So you gained an additional factor of 10. And these 2.5 microseconds, this was due to the fluctuations that the first driving field introduced, actually. Okay? Without this, the lifetime would have been even shorter. And now we gained another factor of 10, and we could in principle switch on additional fields and push this higher and higher. So that's sort of the ideas behind the device. But what can you do with it? Well, you can actually attach spin labels to biological systems, and then you can follow the evolution of these spin labels. And by evolution I mean you follow their position in space, and then you can actually follow the dynamics of proteins, for example. You can also take solid state implementations of quantum information processing, such as nuclear spins, and you can measure individual nuclear spins in your device. Not only the position, you can also read out the spin state, actually. I'm not going to explain you how, but it is also possible. And again, you will benefit from all these decoupling techniques, because it gets rid of all the noise that you have in your environment, and you really only sense the spin that is there. Okay. 15 minutes, oh, that's fine. Okay, so these are the applications. So I mean, I think there's a wide array of things you can apply this to. I'm particularly excited about biology because this would really be first time that you can take individual biological molecules and follow their evolution, and that's quite exciting actually, because you can get rid of a lot of the uncertainties in experiments that just come from the fact that you have ensembles and you have to average and you don't really know exactly what you have there, and the different proteins might interact here. You can look at its individual one, which is rather nice. It can also be used for all sorts of other any magnetic sensing task that you can think of. This may benefit it. Let's put it that way. Okay. Well, that's well, these are the examples here. I mean, you have protein, you have spin labels, it changes its shape. You can follow that and things like that. Right. But I told you that at the moment we are basically reduced to making these color centers somehow, and then we try and find them in a relatively narrow spatial region. But the exact positions are not very well defined. So you can make one, that's great, and that's good enough for sensing. But if you, for example, would like to dream of taking something like this and build a quantum simulator out of it, then you need many of these NV centers, and they have to be spaced in a regular fashion. And as I said, in principle that's possible. And what you would like to achieve is that these color centers are maybe regularly spaced with a distance that is not more than 10 nanometers apart. And then you can start and think, how can I make those color centers interact with each other? So what you want to do is, so you have 3 degrees of freedom here. You have the nuclear spin, you have an electron spin, and you have the optical transition. Optical transition is mainly for readout. Nuclear spin state lives very, very long, can be seconds, but it doesn't couple very much. Electron spin suffers decoherence and all that stuff, but it couples much stronger, much more stronger. So what you want to do is, you want to somehow take the nuclear spins and couple them via the electron spins. And in addition, what you also want to do is, you would like to protect the electron spin during this operation from the fluctuations of the environment as much as possible. And so it's again the same theme. So we apply certain control fields to protect the electron spin and the nuclear spin as well, actually, from fluctuations. And at the same time, under this protection, we want to apply quantum bits. And so that's the idea, and that's how it looks theoretically. I mean, if you do this, I'm not going to explain the details because it's not very nice. We were extremely fortunate, I have to say, because the fact that initially we just tried to protect actually the spins from the fluctuations and thought, let's see what we can get as a coupling strength. And initially it turned out in the end that without this decoupling, you get very, very slow coupling rates of 1 per second or so. So this decoupling techniques actually remove some destructive interference in the system and accelerated actually the evolution. And so what one can do is one can put two spins, 2 NV centers that are 10 nanometers away. One can get about 100 hertz of interaction strength, and for such an interaction strength you get, I've forgotten the precise number, but I think it's 99% fidelity or something like that, which is really rather a good result. And so if you think now you can try and arrange not only pairs, but you have a whole assembly of these nuclear spins, you could dream of putting them in a specific lattice shape, for example. So, I mean, if you can implant them in a controlled fashion, then you can make single cubic lattice, you can make Kagome lattice, all sorts of nice lattice structures. And on those structures you have spins that are interacting with each other. So that's exactly what you want to achieve if you want to make sort of a quantum simulator for quantum spin systems that have interesting properties. Okay. And so, in principle, these decoupling techniques, together with good fabrication, of course, might be able to achieve that. And so, I mean, it's going to be a long road for sure, but I mean, we we are actively pursuing these ideas both in theory and in the lab in Ulm. But given that I have a few minutes, so these are actually extra slides, so to speak. There are 3 extra slides, in fact, so just in case the chairman gets nervous. And here I want to briefly mention another concept that you often will need in quantum simulation. You can build a device where the spins are interacting with each other, and that's great. But actually, if you want to do interesting quantum simulations, usually you have to start out in a very low entropy state. So, I mean, in the ground state, for example. So you have to cool your system, your spin system, to its ground state. And then things become interesting, or at least there should be no entropy, so no noise. And the question is how you do this. So, I mean, here we thought about this initially in ion traps. Well, you can make all sorts of spin systems there, but you have the challenge always that you have to cool the spins to very low temperature. And in general, this is a challenge that you have to address. I mean, you heard, no, I'm not sure you heard, you probably will hear about optomechanical systems on Friday. And, yeah, you did hear. So Czesław Bruckner spoke about, did you speak about optomechanics also?
Yeah, part of it.
Yeah. So there, of course, what you want to achieve to do these wonderful experiments that they're proposing, you need to achieve low temperatures. You need to achieve low temperatures for very heavy oscillators in that case. So just the goal of trying to remove entropy from the system and bring it to low temperatures is an important goal. Now, the standard approach that is being used in that way, towards this end, comes, well, I think originally it was from ion trap physics probably, where the idea is you have a system that has a vibrational degree of freedom. Think of an ion, for example, that is moving in a potential, and you have some electronic degrees of freedom, might be spin degrees of freedom or optical degrees of freedom or so. And you have light at your disposal, so you can shine light onto the system, and what you want to do is you want to dampen basically the motion of these systems. And so this is how this would look like. So these are 2 energy levels when you have 0 phonons in your system. These are the 2 energy levels of the system when you have 1 phonon, so they're a bit higher, both of them. This is for 2 phonons and so on. Yeah, so you form a ladder. So this is ground state of the electronic degree of freedom, excited state of the electronic degree of freedom, and in this direction you have the motion. And so now one really great technique that you can apply is so-called sideband cooling. So you take a laser that couples the ground state of the system to the excited state, and you actually make its frequency a little bit too low. Yeah? And actually you make its frequency lower than the transition frequency between these 2 energy levels by exactly 1 quantum of the motion. And so then what will happen is that if the laser photon comes along and it tries to excite the atom, but it can't because it doesn't have enough energy, so it will take 1 phonon from the motion, use this to excite the system, and so therefore we have now reduced the energy in the motion of the system. And what subsequently can happen is that there is spontaneous decay, which actually falls down from here to here under the right conditions. And so let's say we start here, so you are excited down here, you fall down here, you are excited by the laser here, you fall down here, you are excited here, you fall down here. And when your ion or particle is not moving anymore, that's when this process stops and then you're stuck here. Okay. So that's a fantastic idea, and of course it's an absolute workhorse in ion trap physics. And it works under one particular condition. Namely, the intensity of this field should be sufficiently small. Sufficiently small means the Rabi frequency, in fact, so the square root of the intensity, has to be much smaller than the frequency of the motion. Why is that? Well, if the intensity is strong enough, then you would not only make this excitation, you can also make then off-resonant excitations. So you can actually go here, or you can even heat up the system. And so, by energy conservation, of course, this is the dominant transition, but it becomes less and less dominant the more intense the laser is. And so at some point, actually, I mean, you see when you go through the calculations that really you should, the limit to the cooling speed is essentially the frequency of oscillation in the system. Okay, that's because we have used one principle of physics, namely energy conservation, basically. Energy conservation somehow, in the end, helps us here, but it also works only when we take this limit in place. And now I want to show you that you can cool infinitely fast if you like. And that is by using a different physical principle. Now let's forget about energy selection. And we will actually, effectively we will use interference. So we will design actually a new Hamiltonian. And so the very basic idea I show you here. So here you have your particle. It can move in space. In a moment it will move in space. And it also has here, this is sort of a spin degree of freedom, for example, so that you can attack by light. And what kind of interaction that we have already is that the spin degree of freedom couples to the position of the particle. So that's sort of known. I mean, that's what you can do with simply with a laser. Now what we want to do is, we want to actually generate a new type of interaction. So we want to go from x, sigma x, to p, sigma y. And if we have those, then we can concatenate them together, and I will explain it in a moment, and you get what you want. So how can we fashion this into an interaction with momentum? Well, we take this particle, we kick it by a laser pulse, so now it starts to move. It was kicked, gets momentum, and it starts to move in this direction. So it's displaced in space. And then when it's here, I mean actually here, we'll apply another pulse in the opposite direction. So it stops. So what we have achieved by that is that we have made a translation in space. Yeah. Everything else is unchanged. Equilibrium is unchanged, everything. So we have translated the particle in space. Translation in space is generated by momentum. So really what we have generated as an effective Hamiltonian here is actually the momentum operator. Okay, so that's the idea. Now you can see this procedure, of course I can do very fast. I can hit it very, very hard with my laser. It will move very quickly to here, and I stop it again, and I have generated this momentum state. So in principle, if I have enough intensity in my laser field, I can make this process very fast. And so I have two contributions then. I have this contribution from the original interaction. I have the one that I generate. And because I can, both of them I can make as fast as I like. I can also trotterize the time evolution. I can do this for a short moment, that for a short moment, and I repeat this many, many times. And then I get a new Hamilton operator, which is just the sum of the two. And that allows you actually to make a perfect sideband cooling Hamiltonian in arbitrarily short time. And that can be applied, for example, in optomechanics as well. It's also just a system that has some degree of freedom and is moving. And you can show that, in principle, you can take an object that has 10 to the minus 10 kilos of mass and a frequency, in this case, of eigenfrequency of 10 to the 4 hertz and some other parameters, and you can cool this to the ground state. And that's quite a feat, because here we assume that we start at room temperature. And room temperature is an unbelievable number of phonons in this system, because it only has an eigenfrequency of 10 to the 4 hertz. So that's a way of using actually a different principle and basically interference and Hamiltonian design to actually achieve very, very, very fast cooling. And with that I want to stop basically. So I mean, so what I wanted to show you is basically we can use coherence, interference, dynamical decoupling and so techniques to control the dynamics of quantum systems to make them do work for us, namely either sensing at the extreme limits or individual nuclear spins, or building quantum simulators, or perhaps also quantum information processing. Okay, and this is the, well, people that do the work and the funding. Okay, thank you.
Do you have any questions?
Just on that last point, that's super fast cooling.
Yes.
That sounds really cool. Do you also require? That was terrible. Do you also require fast spontaneous emission as well? Do you need some non-Hamiltonian process to reduce the?
Yes, actually.
To increase the purity.
So of course there is still a speed limit, because at some point you have to get rid of the entropy from the system. And just shuffling stuff around is not enough. But here, in principle, we don't even need to be in the resolved sideband limit. So we can actually have a transition that radiates very strongly, and we can use these methods, and we can then make use of this strong decay. And so it's limited, of course, it's limited by the decay rate of the system. And in the optomechanical system, it's the same thing. There you have in the mechanics, then you have a cavity, and the cavity leaks out in the end the light again. And normally when you think just of sideband cooling, the cavity decay rate shouldn't be much stronger than the vibrational mode. And here, actually the numbers, I think, these numbers actually, are rather significantly out of this limit. It's a factor of 10 to the 5 outside of this sort of normal sideband cooling limit, and that allows you to cool very, very rapidly to the ground state. But it's right, it's not really infinite, it's just very fast.
Anyone else?
Question for non-specialists. The dynamic of decoupling, how does it compare to outlet-on splitting of the transition? We know that if we send strong enough light to level, it splits, it starts to meet the ground cycle state.
Right.
How does it compare
Well,
to
this is basically what...
It's outlet-on splitting.
in principle, I would say, this continuous driving is really about, it creates a splitting of these energy levels. So I would say it's the same thing in the end, but used for a different purpose.
Okay, we have no more questions. Let's